right, didn't get any questions via email that need to be answered during these office hours, nor did I don't really see anyone in the chat. So probably gonna be a quiet one day, which is weird because your exam starts this weekend. So just a quick note on the exam. Opens Thursday at 12:01 a.m., closes Sunday at 11:59 p.m. This does not mean you can start the exam at 11:59 p.m. It means the exam shuts off at 11:59 p.m. So there is a built-in feature in Blackboard. And what this feature does is it says that, let's say I am giving you, so we're not hypothetically, I'm giving you 75 minutes to take this exam. So 74 minutes before 11:59 p.m. Sunday, you start the exam, it's going to tell you can't take it. And the reason it's going to tell you can't take it is because you can't take the full 75 minutes. You're supposed to be thrown out of the exam at 11:59 midnight. So when it comes to taking the exam, I would not recommend waiting until Sunday. I would say take it Friday or Saturday if you can, and do Sunday as an absolute last resort. The Sunday is more meant for people that genuinely can't do it Friday or Saturday. Now, a few comments on the exam. I can see Blackboard login. So if you sit back and you check the Blackboard, check Blackboard Sunday and go, ooh, I don't see it. And then you see me an email at 11:50 that night going, oh, I can't see it. I'm having technical issues. I know you logged in that day and had technical issues. So if you have technical issues, you need to send them to me ASAP. I will sort of be around Friday and Saturday to take care of any technical issues. I will try to get to them addressed, particularly before 9 o'clock. That said, Sunday, if you have technical issues, not much I can do for you, and I'm not likely to grant you an extension because you did wait so long to take the exam. Technical issues do come up. That's why it's important to let me know that you're having them. But again, if you log in first thing in the day and go, oh, I don't see it, I'm not going to shoot an email, I'm pretty sure somebody else already did. Do not go on that assumption. That is not an excuse for getting an extension. Once you log in and say, hey, I can't see it, that's when you need to send me an email. Now, I will probably stop checking emails about 7, 8 o'clock Sunday night just for work-life balance. That said, if you log onto the course website at 10 o'clock Sunday night and you have a technical issue, that was a personal choice to wait until Sunday at 10 o'clock. Not going to grant you an extension for that, so please take the exams early. Another thing to note on the exams, you're going to submit work. Blackboard is just going to give you a grade. And unless you got the answer right in the formatting it's looking for, it's going to give you 0 points. What I'm going to do is I'm going to take your work, I'm going to compare your work towards your answers. You have to have work in order to get points for the question. So if you just happen to get it right and there's no work, you're losing everything but the 1 point you get for the right answer. If you see your grade and go, oh my God, I didn't do so well, wait until you see I have graded the work. So the work's going to give you a score out of 1 out of 1 if I've graded it. If I haven't graded it, it's 0 out of 1. If you send an email saying, oh no, I think I did so much better and I haven't graded your work, I'm probably not going to answer the email because I haven't graded it. Wait until you see that the work has been graded, that the partial credit has been assigned for any work in the event that you didn't get the right answer, but you still had the right work. Then come ask me questions. But again, I'm not probably going to grade these this week, and I will probably wait until Monday and actually go through them line by line. I have something better than this laptop to work on for doing that. But until you see that 1 out of 1 on the work, because that work doesn't count for any points, but it's what I'm used to fill in the partial credit for your exam. If I haven't looked at it, there's no point in sending me an email because I haven't checked it yet. You need to argue your grade after it's actually been looked over and graded. And I typically try to get these graded within a day or two because I do realize, particularly on the summer schedule, we're moving really fast, and I want to make sure that you have time to look over it. So the key should release. I have one student that needs an extension, so it's probably not going to release Monday. It's going to release Tuesday instead. But again, like, wait until you actually see that your work's graded to begin to contend your grade. At that point, you're going to have a bit more of a meritus case. And that's really the only comments I had for today. Again, I got the chat window up in case you got any questions. You're free to ask them about Chem 1, Chem 2, Orgo 1, Orgo 2. These are just office hours. There's nothing really scheduled for this. Morning, Dia. How are you? Dia or Dia? I guess I should actually ask you how you pronounce that. I do apologize if I'm pronouncing it incorrectly. I'm doing well. I'm gonna go give blood after this, so it's always a good night's sleep after I give blood. I've got a rare blood type, so it's like kind of nice to actually kind of get back in that way. Okay, thank you. So it's Dia. What are you up to today? So the Rolle's law is basically a way of estimating the vapor pressure if you mix two liquids together. And honestly, in CE lectures, I like making fun of engineers for this because this really is a dumb law. So let's say I have a mixture of acetone and ethanol. And I'm going to make acetone my principal component. So I've got a mole fraction here of acetone. And on my y-axis, I've got the vapor pressure of the mixture. Well, if I have pure acetone, this is just going to be the vapor pressure of acetone. And if I've got pure ethanol, I'm assuming it's lower. Then with no acetone, I expect it to have the vapor pressure of ethanol. Rolle's law says, well, I don't know anything else, so let me just draw a straight line, and I'm just going to assume that it's a linear average of the two. So basically, it's your way of estimating what is the vapor pressure of a mixture of liquids to get an estimate for what the boiling pressure is. So how low does the pressure have to get before it begins to boil? Now, this is always wrong. I mean, there are almost no liquids that obey this behavior. What we really have are what are called positive deviations and negative deviations. And these are addressed in the notes. You don't have to know how to do these types of calculations, but just be aware, Rolle's law is just wrong. But if you don't have any other information, it's not a bad approximation. Now, we get positive deviations when they're strong. Basically, there's good adhesion between the molecules. We get negative deviation when there's poor adhesion. So ethanol acetone probably takes this positive deviation. Negative would be something like hexane and ethanol. Like they mix, but they really don't want to mix. But the tip-off that you're using Raoult's law is that it'll say like, what's the vapor picture? What is the vapor pressure of a mixture of? And that's when you implement Raoult's law. You're welcome. Do you have any other questions? To the best of my knowledge, no. I don't think you actually need a graph to go along with the tables. I mean, the table graph does imply graph comes directly from those tables. That said, if it marks you off for it, let me know and I'll give you the points back. Sure. So what's your questions? So the XX here is not referring to the final answer. So if you see it says for atomic weights. So it's not saying your final answer should only have one decimal point. It's saying that when you do molecular weights, you should only use one decimal point in the atomic weight. So the reason I do this is that if you look at something like oxygen really weighs 15.9998 AMUs. But let's say you did 16 instead. As you start running these calculations, particularly when they start getting more and more involved, you're going to find that you get what's called machine error. And this is back from old original mechanical calculators, but basically what happens with machine error is that because you've got these slight differences in your numbers, these differences are going to start compounding to the point that you start getting radically different answers, even though you start from very similar starting points. So the reason why I say just stick with one is that every periodic table gives at least one decimal point, but some periodic tables drag them all the way out to 4 and 5 decimal points. Some periodic tables only do one. So for the atomic weights only, use this 0, and this is going to get rid of any machine error associated with any calculations you do regarding molecular weight. Now, for the final answers, that depends on the problem. So let's say you're given some problem and it tells you have 1.6 grams, 1.3 grams, 1.639 grams, 1.639, 2 grams. So these are 4 separate problems. So for all of these problems, you're going to have to look at what's in the actual problem statement itself. If your answers are only given 2 sig figs, then your answer needs to only have 2 sig figs. So let's say the answer ends up being 2.913968. In this case, you would put 2.9 as the final answer. This has 3 sig figs, so if this was the starting number, we'd give it 2.91. This is 4 sig figs, so we would give it 2.914. And for this one, since there's 5 starting sig figs, we give it 2.9140. So the data given to you in the problem is going to tell you how many sig figs you would need to give in your final answer. But the atomic weights we're going to limit to 1 sig fig, not 1 decimal point, not because there is a good argument for it. It just makes it easier to figure out what the answers could be. Because if you do try all types of iterations, you can try, particularly for complicated problems, you can get really scattering answers. And if you do email me, I can take a look on my side to see if you're even getting the right answer. Don't burn up your submissions. With everything but multiple choice, you get 5 submissions for this very reason. Multiple choice, obviously, if I give you 5 guesses on a 4-question multiple choice question, you should be able to figure it out. Yeah, you're welcome. Other questions out there? So for the freezing point, I think there ends up being, if I remember correctly, if you watch temperature versus time, you should get a plot that looks like this. And you have to draw a line through it in order to estimate what the freezing point temperature is. So there should be a straight line here. This is the heat capacity of the solid. The slope of this one, it's the heat capacity of the liquid. And the intersection of the two gives you the freezing point temperature. But you don't have to upload that graph. I think you just have to upload the data sheet. Yeah, we're kind of seeing, so recently, like as of this summer, Carolina Biological changed their labs on us. So this is why you're kind of seeing a little disconnect between the WebAssigns and um, tell you what, let me bring up that lab assignment before I start making any more comments, because I were probably thinking of what we do in the seated lab. But yeah, this summer they changed some of the labs on us, so you're going to see a slight disconnect. It takes time to reprogram WebAssign, and we didn't find out till like 4 weeks ago that they changed this on us. Yeah. So it tells you to record the temperature versus time. And that should give you a plot. So starting about 65 degrees C. Oh, wow. I can't believe they told you to do that. That's terrible advice. Okay. So it talks about it doing this. And it says the last 4 points are the freezing point. So go with that. Follow what the directions say. This is not how we do it in a seated lab. So it wants you to submit the data. If you, during the regular semester, we actually do vanillin and tert-butanol. And the way we teach that lab is that you have plots that end up looking like what I drew, and you have to do 2 lines. Apparently, it's what it's saying for your lab is saying that the last 4 points, that's the freezing point. So that's why there's no graph. Okay, that's okay. It's a home lab kit. Take what you can get. Mostly it wants you to upload data so there's evidence that you just didn't make stuff up. That's the big reason why it's getting you to upload the data. Yeah, we'll talk about the right way. And I'll try to draw a bigger, easier to see graph. So if you do calculus, the change in temperature of a material versus time is related to the rate of cooling. So we're going to assume here that the rate of cooling Q is constant, and Q, the actual dt here is, so Q is mass times the heat capacity times the change in temperature. So what's happening is that the slope of this line, it should be a linear line, is proportional to the heat capacity Cp. So the slope, I'm going to scribble here, goes as the heat capacity. It also depends on the amount of mass. So we expect the liquid to have a certain heat capacity, and we expect the solid to have its own heat capacity as well. Now, what will happen is that we'll get an intermediate range. And this intermediate range here is where we have both a liquid and the solid. And I'm sure there is a proof for this. If we extrapolate the solid cooling curve and extrapolate the liquid cooling curve, their intersection here should be the freezing point. And I think it basically boils down to, it represents the average between the start freezing temperature and the final freezing temperature. So it begins to pull away here when it starts to freeze. Moves over here when it finishes. So this is the way we would do it in a lab. Now, this is a very crude approximation. It does actually give pretty good results, all things considered. Now, that said, the way we would actually do it in a true experimental lab, so I'm just going to erase this part, is where we use what's called differential scanning calorimetry. So what we do is that we would take the solid and go to a liquid. And so if we looked at temperature versus time, and we applied constant heat, little q, because it's a rate, we see that the temperature of the solid increases to a point and then it holds constant, and that's the melt. And then we would see it go up again. The slope here is related to the heat capacity of the solid. The slope here is related to the heat capacity of the liquid. And this temperature here where we see the flattening, because we have latent heat, that's your freezing point. But a DSC runs about $25,000, so we ain't using one of those. So there's what you're doing with the home kit, which is basically saying you're going to cool it until it becomes a solid, and you're going to measure the temperature right after it becomes a solid. That's approximately the freezing point. In the lab, we would measure both the liquid and the solid cooling curves. We would try to figure out where those slopes intersect, and that would give us a little bit better approximation. And then if we had a real lab, we'd actually run a differential scaling calorimeter, a DSC, and we'd figure out at what temperature we see this flattening due to latent heat. So yes, heat capacity is different between solid, liquid, and gas. So gas, they usually run about, I think it's 3/2 the ideal gas constant for an ideal gas. Yes, definitely liquids and solids have different heat capacities. I think generally speaking, the solid has a lower heat capacity because the liquid can move around. So your heat capacity is a reflection of your ability to basically put that heat somewhere. Liquid molecules have translational energy, so the molecules themselves are moving. If you heat them up, they move faster without increasing the temperature. So there's more places for that energy to go. Whereas for a solid, the heat capacity should be lower because the atoms are fixed in the crystal. So the only thing the heat can do is create vibrations. And then gases have a ton of translational energy, which is why their heat capacities are generally pretty high. And look at that heat capacity of an other gas. Getting emails today too. Other questions? So hydrogen bonding only occurs with oxygen, nitrogen, and technically sulfur can do it, but sulfur doesn't like to do it. So when we see we have H bonding, generally we've only got oxygen and nitrogen. And the reason we have this with just these two atoms is because they contain a lone pair. So I'm just going to put an R here to designate that there's something hanging off. And the way we draw this is that the oxygen lone pairs attack the hydrogen, break the hydrogen-oxygen bond to give us what looks like hydronium. And nitrogen is going to be the same way. So the nitrogen lone pairs attack the hydrogen on one of the nitrogens, and we end up forming this ammonium complex, NH3 plus and RNH negative. So really it's only oxygen and nitrogen that can do this because one, they have the lone pairs to attack, and their bonds between oxygen and hydrogen aren't that strong. HF, HCl, HI, all those can technically also do hydrogen bonding. HF in particular can do it, but it's not really fair to call it hydrogen bonding. I mean, it is, but it's not hydrogen bonding in the sense we think about it. For hydrofluoric acid, it's the same effect. One of these lone pairs attacks the hydrogen, and we end up getting H2, F plus, and F minus. But it's Lewis acid-base chemistry. So if you're looking up the explanation, it's Lewis acid-base theory. And typically oxygen, nitrogen, yeah, to an extent, fluorine will engage in this acid-base behavior. Glad to hear that. The origins of hydrogen bonding are much more, you're welcome, they're much more organic chemistry. So we tend to stay away from some of those arrows I drew were mechanistic arrows. We try to kind of stay away from those at this level, but yeah, that's the actual explanation. Connection between molecular weight. So this is something that showed up on the homework. It's going to showed up on the discussion board this week. So for any of these problems, so I've got osmotic pressure pi equals trim TR I big M, and delta T equals K, and I'm not going to specify freezing or boiling. It's the same approach, I M. So for both of these, we've got a unit of concentration, and for molarity, we've got its moles over volume of solution. But moles here is just the grams divided by the molecular weight. So we can plug in here I equals TRI, the mass of the material over the molecular weight times the volume of the solution in liters. And for molality, it's the same thing. For molality, it's moles per kilograms of solvent, which is just grams of solute over the molecular weight times the kilograms. So we get K, I, G over MW times the kilograms. So in both of these, we can directly find a formula that tweezes out the molecular weight. Now in practice, this is just a daunting set of algebra. So what you definitely see with the homework is it asks you for molarity and molality first, and then you kind of get down to this point where you say, well, molarity is just the grams of solute divided by its molecular weight times volume, and molality is the grams of solute divided by its molecular weight times the kilograms of solvent. So it's just algebraic rearrangement. The only thing you would need to know is the grams in the volume or the grams in the mass and the actual pi and delta t's, which you can all do in the lab. You can make the solution, you know how many grams you dissolved, you know the volume of the solution you made, and you can measure the osmotic pressure. Or in the lab, you know how much solvent you use. This is the freezing point lab that you're doing right now. You know how much solvent you use, you know how much solute you added, and you measure the delta T. Correct. The solvent we don't care about. We're trying to find the molecular weight of the solutes. Other questions? I know I'm like texting responses to people, emailing people. I'm glad when y'all show up though. It does actually give me something to do. Okay. Let me just check your previous answers really quick. So you're really close. So for this one, it's 3.936. So it gives you in the problem statement 12.30. That's 4 sig figs. So you need 4 sig figs here. And then for the one beneath it, you're kind of off. So you've got the right number of sig figs. You got the 3. I'm not sure what's going on with your answer because you got 3.97 and the answer is 3.90 or 0.390. So I think you're in the ballpark for 5. But you got 3.397, it's 0.390. But otherwise, it looks like you understand the material. Yeah, usually when you're that close, like it's just some little nuance. But if you're that close, odds are you understand the concept. Yeah, doing well. Doing 152 this summer, and then we're doing 251 this fall and 151 this fall. Upside is like we're actually doing like in-person exam. Well, okay, we're not doing in person. We're doing proctored exams for the fall, so none of this online exam anymore. Should be interesting. So for y'all who don't know, this is Elijah. He took me for Chem 2, Orgo 1, and Orgo 2. And I did check. I have actually had one student who's taken me for all 4 levels of chemistry. So Chem 1, Chem 2, Orgo 1, and Orgo 2. But Elijah is one of those many that have taken me for 3 of the 4 courses I teach. It's good to see you again. I hope you're doing well. And you're always free to come crash these. So generally speaking, the homeworks I can give you some really ridiculously hard problems. Um, so an example of this is when we start doing acid-base chemistry, I can give you something that has a mixture of, or equilibrium. Equilibrium is the best example of this. I can give you some absolutely nightmarish, like double quadratic equations to solve. But if you can do double quadratic equations, you can definitely solve the simpler, like more practical problems. Yeah, I'll see you later, Elijah. So what you're going to find with the homework is particularly, so if you look at a typical homework set, the first problems are easy, the last questions are much harder. Typically the test questions sit around the middle part of that homework assignment. So the ones that are harder than the first problems, but definitely not as hard as the later problems. Um, but the reason being is that in an exam you have 75 minutes. But I also like to kind of give you the hard problems to demonstrate that it's more tedium than anything else. It's not like the concept got harder, you're just having to apply it in more and more nuanced ways, but the basic concept hasn't changed. All right, so unfortunately it's 11:59, I do need to take off. Again, don't forget your exam opens up tomorrow. Take it as soon as you can. Email me as soon as you have issues. I will try to be around to deal with any type of technical issues you have showing up. And other than that, I will see you all next week.